All right, I guess we could get started now. Hello, everyone. Good afternoon, and welcome to the Clean Water Conversation series. Thank you all for joining us today. My name is Julia Rastelli, and I use she, her pronouns. I am an Eco-AmeriCorps member serving with the Clean Water Initiative Program at the Vermont Department of Environmental Conservation, and I'll be facilitating today's conversation. Our speaker today is Dr. Matthew Vaughan of the Lake Champlain Basin Program. He will highlight preliminary data on the water quality impacts of the July 2023 flooding on Lake Champlain, compare this data to a typical year and to Tropical Storm Irene in 2011, and discuss how high flow events like the July 2023 flooding factor into Lake Champlain's phosphorus pollution reduction targets. Our next clean water conversation is on Thursday, April 4th at 12 p.m. Stacy Pomeroy and Ned Swanberg from the DEC Rivers Program will introduce the science, policy, and regulatory work of the River Corridor and Floodplain Protection Program. The link to register can be found on the Clean Water Initiative Program website and will be added to the chat at the end of today's presentation. Today's conversation will begin with a presentation from our speaker, followed by a question and answer period. You can write your questions in the chat and I will read them during the Q&A, or you can raise your hand during the Q&A to verbally ask your question. This conversation is being recorded and will be made available on our YouTube channel. With that, I will turn it over to our speaker.
All right, thank you very much for that introduction, and thanks for the invitation to speak today. Looks like we have an awesome group of folks joining us. I was really excited to see a lot of familiar names on the registration list, so thank you for joining. I'm going to try to share my screen here. All right. How does that look? Good?
Looks good.
All right, cool. So yeah, my name is Matthew Vaughan. I'm the Chief Scientist at the Lake Champlain Basin Program. And I'll be talking about the July 2023 flood and what we've learned from our monitoring efforts in the months that have followed. So just an overview of what I'll cover here. I'm going to talk about the rain that we saw, the flows in our rivers as a result of that rain, how much phosphorus moved downstream, the lake level, what happened with Lake Champlain, and then the lake water quality. So for each of these, I'll be, reviewing the observations we have and statistics to compare this to what we typically might see in a normal year or without a flood like this. How it compares to Tropical Storm Irene, which is, recently on a lot of our minds, and then also how it compares for phosphorus loading for the total maximum daily load, or kind of the annual budget for phosphorus loading to Lake Champlain that we're shooting for. I want to start with a few things. First is I want to discuss what I'm not covering in this talk, really important topics that I don't have time to get to today. First is the loss of life and property with this event. This is a major event that impacted a lot of our communities with devastating impacts. So that is not the focus of this talk, and that is covered elsewhere very well by the media, and the state has coordinated relief efforts for our flooding recently. Displacement and evacuation, similarly, not covered in this talk. Farms had a lot of crop loss and contamination issues. Infrastructure damages, major problems with this flood, not covered in this talk. And then wastewater discharges and overflows. If there are questions at the end, we can cover this, but it's not the focus of what I'll talk about today. And then the other big asterisk I want to go over is that these results are provisional. The talk I'm going through today, I prepared in the fall of 2023, so a few months ago now, and all the data was still pretty provisional. It hadn't been fully approved, so I do expect that a lot of this will be revised, but I think that the general story and the main points I'll be making will still hold true, even if the numbers are revised. So please understand that this is kind of an ongoing process. And a good place to look at the final numbers will be the 2024 State of the Lake report that the Lake Champlain Basin Program will release on June 5th. So look out for that one. Okay, I'm going to show, hopefully this animation will work. Yep, there's a GIF rolling there. This is the radar from July 10th and 11th that just shows how this really unusual storm hung out over the Lake Champlain Basin and eastern Vermont as well for about 48 hours. And there were three main reasons why the storm was so unusual meteorologically. I don't really understand them, so I'm not going to cover them here. But NOAA has, released information on why this was so unusual, and it resulted in a huge amount of rain over a 48-hour period. Here's a map just kind of showing with color the total rainfalls over the 48-hour period. You can see that, if you can see my mouse here, the highest rainfall amounts were really focused in Vermont and along the spine of the Green Mountains. It's a really widespread major event, although in the valley and the New York portion of the Lake Champlain Basin also received a significant amount of rain. So this totaled about 3 to 9 inches over a 48-hour period, which is a huge amount of rain. The highest 48-hour rainfall total was 9.2 inches in Calais, Vermont. Some stats from Montpelier, the daily rainfall record was broken with 5.28 inches, just barely beating the record with Tropical Storm Irene, which was 5.27 inches. The monthly rainfall record was broken with 12.06 inches. Previous record there was from 1989 with 10.69. So really smashed that monthly record for rainfall. And as you all know, this resulted in widespread flooding in the region, especially the Winooski River, the Lamoille River, and Otter Creek reached major flood stages, resulting in inundation of a lot of low-lying areas and causing a lot of damage, as I discussed earlier. There's also flash flooding from smaller rivers and streams. This is an aerial image from Montpelier, and you can just see, this is the bridge spanning what is typically the extent of the river and a huge amount of flooded area here. So when you're thinking about property damage and flood, inundation and kind of short-term impacts of a flood, we think about the stage of the river or the depth of water. And luckily, we have a significant investment in tributary monitoring for stage and discharge. So when I say stage, again, that's the depth of water. And if you're like me during this flood or any major event, you are glued to these forecasts that NOAA puts out. This is a hugely valuable resource for our emergency responders and for our communities, where you can go on and look at many of our tributary gauges, these are highlighted here. Our major gauges are highlighted with these little pin marks here on the map around the lake. And you can see that they have a forecast for how high they think the river might go given the current state, the saturation of our soils and the watershed, and the rain that's forecast to come in the near future. So you can see it's also kind of partitioned to major flood, moderate flood, minor flood, and action level here. And for Winooski River at the Montpelier, obviously we're in the major flood territory. So again, in the short term for infrastructure damage, we're thinking about how high vertically will the river go. When we're thinking about water quality impacts down the road or in the short term, we're thinking about how much water moved downstream. So it's a different concept, but it's related. And I won't get into how that relationship is made, but moving forward, I'm going to be talking about the volume of water per unit time. So in this case, thousands of cubic feet per second. And this is 19 of our major tributaries to Lake Champlain, all added together over this about week period, and looking at, again, the thousands of cubic feet per second moving into Lake Champlain. And the highest point during this storm, or following the storm, was in the evening of July 11th, and the instantaneous or the highest peak flow for the storm was almost 110,000 cubic feet per second. So that's kind of, if you convert that to gallons, that's about, there are almost 4 billion gallons of water every hour flowing into Lake Champlain. A huge amount of water as a result of the storm. Now here's a very similar graph. This time we're looking at the daily average over this week period, and I've kind of colored the graph by the different tributaries that are contributing water to during the storm to the lake. And the reason I'm doing this is to show that over this week-long period, the top 5 tributaries, Winooski, Lamoille, Missisquoi, Otter, and Saranac, together delivered about 80% of the total amount of water. So this was really, driven by our large tributaries They contributed about 219 billion gallons of water, or 829 million cubic meters. Again, a huge amount of water, and really driven by our large tributaries, which is not unusual for a storm like this. Our large tributaries really are driving the water and nutrients being delivered to the lake. So I want to share some statistics dating back to 1990 when our long-term monitoring program began. So for July 11th, 2023, the daily average flow was greater than 90th flow percentile for all of our tributaries. So not surprising, this is an unusually large event for all tributaries to Lake Champlain. It was the highest daily flow ever recorded for the Lamoille River. It was the second highest ever for the Winooski River, second only to Tropical Storm Irene. And I'll come back to this point throughout the talk. It was the highest flow ever recorded for this date in July for nearly all tributaries. So this is not only unusually high in general, but especially high for the summer period when flows are typically lower. Here's a new type of graph. Bear with me here while I explain it. So this is a similar concept, kind of combining all water, the volume of water from all tributaries flowing to Lake Champlain. But now I'm showing a line for every year going back to 1991, starting at the beginning of what we call the water year. So the water year starts on October 1st and goes through September 30th. It's kind of like a fiscal year or federal fiscal year you might be familiar with. And the idea there is to not break the winter into two like a calendar year does. So we're starting on October 1st, going through September 30th. This yellow line is the average flow for all of our tributaries going into Lake Champlain. And each of these individual kind of skinny lines are a year from going back to 1990, all of them going back to 1991. And now I'm going to highlight the 2023. So you can see that here, this is in July, right here, this pink line is 2023. You can see it is really high, but it's not the highest flow we've ever seen. It's actually the 13th all-time rank of flows going to Lake Champlain. The other thing I'll highlight is that a lot of the higher flows are in the springtime. Again, it's unusual to see a flow this high in the summer. We typically see our highest flows of the year around the snowmelt period in the spring. Again, I'm going to highlight 2011. In 2011, we had even higher spring flows than in the summer of 2023, and we had Tropical Storm Irene. And this is the same plot, but just more highlighted in the spring and summer period. So again, 2011 in blue, you're seeing, three points that were above 100,000 cubic feet per second. And in 2023, just this one peak in the summer period. So again, a really significant event, but in context, it's not, into the stratosphere compared to what we've seen for other spring snowmelt periods for other years for Lake Champlain. So summarizing here, especially high flow for this time of year, and the average flow is about 7,000 cubic feet per second. So it's much higher than that, up around 100,000 instead. And I want to provide some context for that. I've been talking about the time of year when we typically see high flows. This distribution, or when we're seeing our higher or lower flows, is actually changing for Lake Champlain, for the Lake Champlain Basin. So I'm going to show some plots to demonstrate this. This is a type of plot you may not have seen before. We're looking at discharge trends or water flow trends for the Winooski River. And the vertical axis here is showing whether the trend for the amount of water or the discharge is increasing if it's above this dotted line and decreasing if it's below this dotted line. And the horizontal axis is showing the flow quantile. So the highest flow for a given year is all the way at the one side, all the way to the right, and the lowest flow is to the left. The median or the 50th percentile is right in the middle. And the color here is whether this is a statistically significant trend or whether it's could go either way. It may not be statistically significant. So what we're seeing is for the Winooski River overall, we're seeing significant increases in about the 80th to 90th percentile of flows. So our relatively high flows are increasing for the Winooski River. And we have decreases in the lowest end of the flows and actually in the highest end of the flows too. And so now I'm going to show similar plots, but now they're broken up by season. So what this shows is that for the summer season for the Winooski River, We do have some increases, but they're not really statistically significant over the 35-year time period. And we do see the highest flows in the summer are increasing, which is not surprising, based on these kind of episodic summertime rainstorms that we are now becoming more familiar with. But importantly, during the winter time, we're seeing significant increases in flow. And this is a signature of climate change, where we have less precipitation falling as snow, more precipitation falling as rain. And what I'm not showing here, but is also true, is the spring period is actually decreasing. So we have higher flows in the winter, lower flows in the spring, and then these higher episodic extreme events in the summer that we're starting to see as well. So the distribution is changing over time, even since 1991. We're able to show that with this data. Okay, next I'm going to start. So that was all just the amount of water that fell on the watershed and then moved downstream to the lake. I'm going to shift now to talk about the phosphorus delivery. Okay, using our water quality sampling and modeling techniques, we're just estimating the amount of phosphorus that was delivered to Lake Champlain. So this is a very similar graph that I showed earlier for water, but now again, we're talking about phosphorus in metric tons. Okay, so I broke it up by tributary, showing, and this again is to highlight that for the 7-day load starting on July 10th, when really the storm began, the top 5 tributaries, the Winooski River, Missisquoi River, Lamoille River, Otter Creek, and the Pike River, delivered 90% of the phosphorus over this 7-day period. So all of the other, 13 tributaries delivered the other just 10% of the phosphorus over this time period. They delivered about 359 metric tons, although not all the watershed is monitored, so there's an asterisk on this one. But that's a lot of phosphorus, right? And so if you compare that to the full lake total maximum daily load for an annual budget that we're working for, it's about 60 to 85% of the total maximum daily load. And that depends on how there's a few calculation considerations I won't get into here, but basically I would say that I'm confident that probably more than half of the annual phosphorus TMDL was delivered during this 1-week period. And I'm going to come back to that to discuss how significant that is in context with other years. So I'm going to go through some stats just like I did for flow, but now I'm talking about the daily phosphorus load delivered on July 11th, which is kind of the main day for the storm for when phosphorus was delivered. So similar to flow, this was greater than 90th percentile for all of our tributaries. It was the highest daily load ever observed for the Pike River, which is a binational river, goes through Vermont and Quebec. It was the second highest daily phosphorus load for the Winooski River, second to Tropical Storm Irene. It was the highest load ever for the state for all but two tributaries for this date. Unusually high for the summer period. It's again. And thinking about the full load to the lake, this is the 3rd largest daily load ever recorded for Lake Champlain, going back to 1991, or excuse me, 1990 in this case. The highest ever was Tropical Storm Irene, and the second was actually the Halloween storm of 2019. Many of you maybe remember that one, and the reason that one was a bit higher was because it was a major storm, just like in the summer, but it was focused in some of our tributaries that have higher phosphorus concentrations. So it actually delivered more phosphorus than this July storm last year. And that Halloween storm was significant for me because my roof blew off during that storm. So it's memorable for my family. But yeah, it was a bit surprising to me to see this. That's what the data showed. All right, next I'm going to show the cumulative phosphorus delivered to Lake Champlain for all years going back to 1991. Again, I want to put this into context for you to see how unusual the 2023 flood was compared to other years. So this is similar to a plot I showed before. This is 17 monitored tributaries combined for all years going back to 1991. Again, we're starting at the beginning of the water year, which is October 1st. Each line here is a different year, and we're looking at cumulative phosphorus load. So every day when the rivers deliver phosphorus, this line is kind of ticking up over time. And when you have a storm come through, that's when the lines go up very quickly, right? because storms deliver more phosphorus than times of low flow or base flow. The average is shown in this yellow line here. So you can see that, typically the phosphorus will be increasing, and you'll see it'll go up a little bit faster in the springtime during snow melt periods. And then again, for each individual year, you're seeing phosphorus kind of shoot up with storms as they come through. I'm going to highlight the 2023 year. Again, I did this analysis in the fall, so I don't have the full water year for this presentation, unfortunately, but you can see what I want to highlight here is that I almost forgot this by the time I was doing this analysis because we were so focused on the flood, but we actually started we didn't start the water year, but we started the calendar year with a really dry spring for last year. So we were actually well below average going into the spring, going into the summer for phosphorus delivery to Lake Champlain. So that we're below, this kind of pink line is below the yellow average here. And then when their storm hit, it shot us way above average, but as you can see, with all the variability here from year to year, it did not shoot us into the stratosphere or shoot us higher than anything we've ever seen for an annual load of phosphorus. I'm going to highlight the 2011 line here. So you can see for 2011, we started the water year really, really high. We had some early storms. We had the big spring flooding that caused the historic lake flooding in the spring of 2011. So we were already high going into the summer, and then we had Tropical Storm Irene, which is the biggest delivery we've ever seen since we began monitoring in early 1990s. So this is just comparing the two, 2023 here and 2011 here, and again, compared to typical. So compared to typical or compared to average, we started below the line for the storm, and it shot us well above it, but still not, way out of line with anything we've ever seen for phosphorus loading to the lake. Now I'm going to show you something very similar, but I'm going to break it up by lake segment. So you can see how this compares to the TMDL allocations for each of our, or for 4 of our segments I'll highlight. Okay, so you're seeing, again, the very similar plots. I'll note that the vertical axes are different for each of these because the TMDL allocations are different for each of our 13 lake segments, 12 in Vermont plus 1 that's specific to New York. And the horizontal orange dotted line here is the TMDL allocation. So that's the goal we're kind of shooting for phosphorus loading to each of these segments. We have each line is a year going back to 1991 again, and the yellow line again is the average over time. And now I'm going to highlight 2023 for each of these. So you can see as an example for Cumberland Bay, where we didn't have this, as extreme of an event on the New York side. Cumberland Bay is at the mouth of the Saranac River. We didn't see, much of a shooting up for phosphorus delivery compared to the average at all. So we're still even below the TMDL. So that's a good thing for Cumberland Bay. For Mallett's Bay, we were well below the TMDL, well below the average, and the storm brought us above both of those lines. For Main Lake, same story. We were hovering, right below the TMDL line in the summer for this water year, and then we shot above to the second highest ever loading for the Main Lake, and that's mainly driven by the Winooski River. And for Missisquoi Bay, similarly, we were, for Missisquoi Bay, many of you know that loading is much higher than the TMDL, where this is why it's a focus of so many restoration efforts. And in this case, the loading was above the TMDL to begin with, but below average, and then the storm shot it above average. So this gives you some context for 4 of our lake segments and how the loading kind of relates to the TMDL for each of these for the 2023 water year. Hopefully you're all still out there. Julia, let me know if any chats come in or any questions come in. Oh, right, and I also highlighted the 2011 line again. So similarly showing you that for 2011, we started much higher earlier in the spring, and then Tropical Storm Irene, again, really brought it much higher for each of these segments. So just kind of highlighting the differences there. Okay, next I want to talk about how the July 2023 storm phosphorus load compares to annual phosphorus loads, because I'm sure many of you, if you followed the news on the storm, you heard about how the storm delivered, X times the annual load that we typically see for phosphorus. So what I'm showing you here is the ratio of the seven-day July 2023 storm phosphorus loading compared to the annual loading. So how many times more did the storm deliver in a week compared to an entire year? This is shown over time. And I'm picking the Lamoille River because there was an early analysis of this done, which was correct, that said that the Lamoille River delivered more in a week following the storm than in all of 2022. And that's true. And I think that soundbite got away from us a bit because you can see this is the 2022. It was about 1.2 times the annual load for that year, but that year was relatively dry and a low load, so that ratio is higher. But the Lamoille River during the 7 days following the storm actually delivered about 60% or 0.6 times the typical or median annual load for the Lamoille River. So this is kind of just a useful way to think about this. You know, how many more times of an annual load did that storm deliver over a week period? And for the Winooski River, it was actually a bit more. For that storm, about 1.3 times the typical or median annual load was delivered for the Winooski. And now I'm going to show a plot with a lot of lines here, but you can kind of blur your eyes and just bear with me that this is really showing that for most of our tributaries, the 7-day phosphorus load was about 20 to 50% of the 20 to 50% of the annual load for that tributary. And actually, that's not really that unusual. So now I'm going to show you a plot that shows, again, some context. So not specific to last year's storm, but I want to show you some context to help understand it. So high flows are always important for nutrient delivery. And you can see, this is a good example. I should have mentioned that all of this aerial imagery I'm showing is from Peregrine Productions. They are awesome and had some drones flying out following the storm to get some really amazing and captivating aerial imagery here. But you can see how, there's a lot of sediment, a lot of phosphorus running in this river here. When we have a storm come through the landscape, we obviously have a lot more water running in our rivers. And for each unit of water, we have more phosphorus or higher phosphorus concentration. So the more water and the more phosphorus per water together combined, they have a multiplicative effect. And so that's why we have so much more phosphorus coming down during times of storm flow compared to times of base flow. And that's what this next plot is going to show. So this is kind of a new idea. You're seeing the portion of phosphorus contributed by the Winooski River on the vertical axis, so 0 to 100% or 0 to 1. And the colors represent an amount of time for each contribution. So this shows that the biggest single day for each year, going back to 1991, typically sends about 5 to 10% of the total annual phosphorus load. So a day is only about 0.2% of an entire year, but the Winooski contributes 25 to 50 times more than this of the annual phosphorus load. So again, times of storm flow are really important for any river for annual phosphorus contribution. If you go up to the other colors, this is showing that, for the top 5 years, the highest 5 flow days for the Winooski River delivers about 20% of the annual load typically. And the highest 30 days for a typical year delivers about 60% of the load. So that means all of that remaining 40% of the annual phosphorus load is typically delivered in the remaining 335 days of the year, right? So again, this is all to demonstrate that storms, even in a typical year, are really important for phosphorus delivery. It was not an exception for this July 2023 storm, and it's even more so for a year like this, but it's not unusual that it's a high percentage of the annual load. Okay, now I'll shift gears a little bit to talk about our high frequency monitoring that we had going on during the storm. We were lucky that we've started piloting this program where we have buoys deployed in the Lamoille River and the Mallets Bay, and these buoys are monitoring key water quality parameters at 15-minute intervals all the time. And they are really good at capturing events like this storm because it's hard to get out to all these areas and collect bottles of water and bring them back to the lab. It's much better if you have equipment there kind of measuring in the stream night and day, and holidays and weekends as well. So for this storm, I won't get into details, but we lost contact with this buoy for about 2 days. It was underwater and we weren't really sure what was going on with it or if the buoy was still there. But after the river went down, the flood waters receded a bit, and the modem was able to connect with the cell tower. We got all the data. It had been measuring water quality kind of while submerged that entire time. So we got a really good record of the storm. Luckily, it all went really well. So I'm showing plots of a few things here. This is the Lamoille River discharge, again in cubic feet per second. You can see how the rain caused the discharge to go up over 30,000 cubic feet per second. Again, that's the highest that's ever been recorded for the Lamoille. And then you're seeing the pH, or the acidity of the water, decrease, which is typical during this time period. And this is all measured by the buoy in the Lamoille River at a 15-minute interval, 4 times an hour. And you can see, this is really typical of storms, that the pH is depressed or goes down over the storm flow. Specific conductivity is a measurement of how many things are dissolved in the water. This also typically decreases with storm flow, and we are able to capture that with the buoy there. And the thing I'll really highlight is the turbidity. This is a measure of water clarity. How turbid is the water? How murky is it, essentially? And we had huge spikes in turbidity, which is not surprising if you see that aerial imagery. All the sediment being mobilized to Lake Champlain, we're able to understand and quantify with this buoy data. And I'm going to come back to this when we look at the buoy that we had in Mallets Bay as well. Okay, so next I'm going to kind of look downstream. That was all with tributaries and our rivers. Now I'm going to look at lake level and water quality for you. So similar plot here. We're looking at Lake Champlain level in Burlington. This is in feet above sea level for all years going back to 1907. So starting again at the beginning of the water year on October 1st. The average is shown in yellow, and I'm going to highlight 2023. It's right here. So we were actually pretty close to average over the spring melt period. And then because of that dry spring following snow melt, we were below average. We had a bit of rain before the July storm, and that brought us right about to the average lake level. And as a result of the storm, the lake rose about 3 feet, which is really amazing. But it did not bring us to flood level, which is 100 feet in this datum I'm showing here. And I'm going to show 2011. Of course, in 2011, we had the highest lake level ever recorded, up at near 103 or over 103 feet above sea level in the spring. And then similarly, it was down at a similar level and was brought back up by Tropical Storm Irene by about 3 feet. So a similar change in lake elevation as a result of this storm last year compared to 2011. But again, it did not cause anything that was actually above flood stage for Lake Champlain. Now a bit on lake water quality. So these are photos from Mallets Bay, and Secchi depth, many of you know, is just a measurement of water clarity. We drop something that looks like a dinner plate into the water and see how far below the surface we can still see the dinner plate. Secchi depth was 0.4 meters on July 20th, which is a bit more than a week following the storm. Typically, it's more like 2.5 meters. And this is a really good indicator of the photic depth, or the photic zone, how far below the surface things can photosynthesize and produce energy for the lake ecosystem through photosynthesis. And so because the photic zone is usually about 2 or 2.5 times the Secchi depth, this is a decrease in photic zone by about 4 meters. And this lasted for about 2 weeks, this depression in the photic zone. So this, certainly had impacts on primary production in the lake and the ecosystem, but those effects were short-lived. And another thing that probably impacted was predation for fish that use sight to hunt their prey, but we don't have data on that, of course. So I'm going to talk about data from the Mallets Bay buoy. Here is a photo of our buoy sitting in Mallets Bay. It's a beautiful spot, and I'm just going to focus on the turbidity data for this one. So again, this is how murky is the water. So the higher numbers in the vertical scale means that it's less clear. There's more turbidity, and so we're starting in July 10th here, which is really when the rain started, and you see a huge spike a few days after the storm, and then it went down and then went back up again. So we can talk about that if anyone has a question, but essentially we're seeing way higher levels of turbidity in the lake than we would typically see. So this brought a lot of sediment from our tributaries and from our watershed. I'm going to combine the turbidity data. So this is from the Lamoille River and Mallett's Bay, putting it on the same plot here so this is kind of the same time scale on the horizontal axis. So you can see the Lamoille River discharge, the flow. Here we had the highest peak in Lamoille River turbidity really, just as the storm began, which is pretty typical when you see that first flush of sediment coming downstream. And then it took about 2.5 or 3 days for the sediment plume to reach the Mallett's Bay site, which is about two miles away from the mouth of Winooski River. So that's a bit less than a mile per day. So with these two systems, we can see, how quickly this sediment plume carrying phosphorus and everything else is moving across the lake. And then this depression, followed by another increase, is likely mixing from other tributaries in the lake as well. And then you also see over about a 2-week period, the turbidity is decreasing as the lake continues to mix and the sediment is settling. And it took, a little over 2 weeks for it to get back to a normal turbidity level in Mallett's Bay and other areas. Okay, so I'm in my summary here. So we had, just kind of reviewing what I've gone over. Actually, I'm going to go back 1 second to just water. I'll say it in the summary. Never mind. Moving forward. We had historic rainfall amounts over a 48-hour period, 3 to 9 inches fallen of rain that fell throughout the Lake Champlain Basin, really incredible amounts of rain. For river flows, we had greater than 90th daily flow percentiles for all of our tributaries, a daily record for the Lamoille River, and a second place record for the Winooski River. And especially this is unusually high for the time of year in the summer, where we typically see our highest flows in the spring snowmelt period. And as I showed, this is consistent with climate change trends, where we're seeing more persistent and frequent summertime rainstorms, higher winter flows and lower spring flows. For phosphorus delivery, this is preceded by a very dry spring. 5 tributaries delivered 90% of the 7-day storm flux of phosphorus. More than half of the full lake TMDL was delivered in 7 days. And again, this is typical for our largest storms to deliver a significant portion of phosphorus load, as I showed. It was especially significant for the main lake, largely because the Winooski River was such a big contributor of phosphorus. And this is also consistent with climate change trends, given the time of year of the storm. For the lake level rose about 3 feet from roughly an average level to a record high for the season, but it was near normal for the spring. And I forgot to mention that the record for, I think it was July 23rd, was set. So again, the time of year was really unusually high. And for lake water quality, again, we had high turbidity. Primary productivity and photosynthesis was likely suppressed as a result of this for a few weeks in the short term. Dissolved nutrients were, likely available for later season growth from this storm. And the thing I wanted to come back to, and I didn't show with graphs, but I can talk about a bit, is that for phosphorus in the lake, what we're seeing is really not a terribly unusual year for phosphorus, because our deeper basins in the main part of the lake are deep enough that phosphorus can settle out from particulate deliveries from phosphorus that's bound to the sediments. We saw a pretty rapid recovery of phosphorus levels, and nothing that was unusual for that time of year. And for our shallow areas like Missisquoi Bay or St. Albans Bay, we saw a bit of an uptick, but really quick recovery for phosphorus levels. And then what we see typically later in the season is that internal loading can be more important for phosphorus levels than these episodic events. So even though we had a lot of phosphorus delivered, the lake is a big system. It can recover, in the short or mid-term. And the real concern with storms like this is the long-term trend, where we're seeing climate change, in some ways working against the efforts that we're making to restore Lake Champlain. But in the short term, we did see, recovery and nothing really out of the usual for cyanobacteria growth or phosphorus levels. And I said we're waiting on 2023 data. I do have it now, and I was hoping to have a bit more of an update on this, but I caught the flu last week and lost some time. So I'm sorry that I don't have more on this, but just I can talk about what we're seeing kind of informally if anyone has questions there. I also wanted to go over what this means for restoration of Lake Champlain and for phosphorus loading. You may know that the TMDL does have a margin of safety built into it. So it does take into account that climate change may, produce more of these extreme rainfall events. And what we're really going for with the TMDL is the amount of loading that will result in the concentration of in-lake phosphorus concentrations. Said that a bit wrong, but it will result in the phosphorus concentrations that we're looking for in the lake to achieve the water quality goals that will, provide things like reduced cyanobacteria blooms. So there was, with the modeling for this TMDL, we have a margin of safety built in for storms like this. We do, as you saw, we have a huge amount of what I call interannual variability, where some years are very high, some years are very low. And that is really driven by the amount of snow that falls and melts in the spring and our summertime, summer and fall rainstorms as well. So what we need to do with our restoration efforts is really bring this interannual variability on a downward trend, but we're not going to be able to do away with the interannual variability. We're always going to have these years with big storms. We're always going to have dry years as well. And that is, ties into climate change. Unfortunately, we're seeing more persistent and frequent storms like this, and our ongoing efforts and projects will continue to provide resilience to these types of events. We saw a lot of projects that were installed as a result of the 2011 flooding hold really well in 2023. And as we continue to restore and repair from 2023, we'll be more resilient for the next storm, which unfortunately will come. So we're focused, all the work that the states of New York and Vermont and the Lake Champlain Basin Program do are really have resilience in mind to prepare for storms like this. And I have some resources here. I think Julia is going to send around my presentation to folks who registered. We have, a brief written summary of the flooding. I wanted to point to our real-time data website, which is not too exciting right now, but because we don't have buoys deployed in the water. But this spring, when the buoys go back in, you'll be able to see real-time water quality data coming in from our tributaries and lake. And then I also want to point to our Lake Champlain Basin Program science blog, where we summarize a lot of the research that we fund in really quick articles for folks who are interested. And that's what I have. Thank you.
Great. Thank you so much. I just pasted the links from today's conversation in the chat, and they'll also be available in a follow-up email along with your presentation, like you said. I can now read through any questions that we have in the chat, and I invite everyone to type any other questions in the chat or raise your hand with the raise hand feature. The first question is, you have tons of phosphorus loading in water. Can you compare that to how much loading is happening on land?
I'm not sure I understand the question. Let me talk a little bit about how we think about phosphorus loading. So, or maybe, are we able to unmute the person and see if they can clarify the question, Julia?
Can you hear me?
I hear you.
Yeah, I just unmuted myself.
Great.
Yeah, I was wondering, you got tons of phosphorus coming down the rivers and in the lake, and how much we know it's supposed to come from agriculture. How much is being spread out in the land compared to how much is being flooded down the waterways?
Okay, thanks. Yeah, I understand your question now. Thank you. Let me pull up one graph I have for you. This may be helpful. This is from our State of a Lake report. This is our 2021 version. We'll be, as I mentioned, we'll be issuing a new version of this June. This shows the sources of phosphorus to Lake Champlain from different types of activities or different types of land in the Lake Champlain Basin. So about 40% of the phosphorus comes from agricultural land, 6% of it comes from wastewater treatment facilities, 16 is from developed lands like our cities and towns and roads and things like that. 18% of it, almost 20%, is actually from erosion of our stream banks. And then 20% is from our forested areas. So that gives you an idea of where phosphorus is coming from. In terms of tracking what is applied to lands, maybe in an agricultural setting, there has been some work there done. Michael Ronan, a colleague of mine at UVM, who's moved on at this point, has tried to quantify, how much phosphorus is being input to the Vermont portion of the Lake Champlain Basin that would eventually, either make its way to agricultural products or to our waterways. And we're seeing that there is an imbalance of phosphorus where more is coming on to the land than is leaving as these products. And we also have a study going on for the Missisquoi Bay Basin to do a kind of mass balance, we're calling it, to try to understand all of the inputs and outputs of phosphorus so then we can focus in on how we can reduce the amount of phosphorus moving into the watershed. So it's not something that's tracked. We don't have our eyes on every single source of phosphorus, but it is a question that we're trying to learn about and trying to understand better so we can focus our efforts.
Thank you.
You're welcome.
We do have more time if anyone else has any questions that you want to either add to the chat or speak aloud. Tobiah?
Hey, thanks so much for your presentation. A quick question. I just wanted to make sure I was clear on the total phosphorus loading that the flooding represented. So I wrote down something. It was one for the Winooski River, 1.3 times the median annual load happened on July 7th. Is that right? Or was that like a flow rate and not phosphorus?
Yeah, thanks for asking. You're close. The let's see, let me try that right. Yeah, 1.3 times the typical median annual load for the 7 days following the July 2023 storm. So from July 10th through the 16th. So if you take those 7 days and add up all the phosphorus that went downstream for the Winooski, it was 1.3 times the typical annual load for the Winooski.
Okay, thank you so much.
Okay, you're welcome. Yeah, and that will be that's in the presentation that will be sent around too. And I know the 7 days is a bit arbitrary. Humans think of a week, but there's no reason I had to cut it off at 7 days. But I thought it was a nice chunk of time to kind of illustrate that kind of flood period. At that point, the rivers were still flowing really high, but I think 1 week is a nice way to illustrate it. So it's not a special amount of time by any means.
No, I appreciate that. I was just trying to get a sense of like how different this was than a usual situation and how much more it was than an annual compare. And you did say something about internal loading can be more significant even than flood events. Can you clarify what you mean by that? I'm not sure what that term means.
Definitely. Yeah. So when I was talking about, how much phosphorus moved downstream from the watershed during the storm, we call that external loading. If you're thinking about the lake, you have multiple sources of where phosphorus can get into the water column. External loading is, being delivered during a storm from the rivers, right? And that phosphorus delivered from the rivers and it mixes with lake water. And if you're a cyanobacteria or other organism living in the lake, you can use that to grow. Okay. Internal loading for a lake it refers to phosphorus that's already there, but it's not in the water column. So for shallow areas like Missisquoi Bay, there is phosphorus that's kind of locked up in lake bottom sediments in the shallow bay. And under the right water chemistry conditions, that phosphorus can actually be released into the water column and be available for growth. So we call that internal loading, and that's phosphorus that was at one time external and settled to the bottom, and it's kind of locked up there. But throughout the season, especially late in the season when we have our hot days with low wind speed, that phosphorus can be released, and that's actually more important in some areas like Missisquoi Bay and St. Albans Bay for driving or cyanobacterial blooms than our rainstorms like we had last year.
Thank you so much.
You're welcome. And yeah, I can share more research on that if you're interested.
This is Dave Johnson from Federation of Vermont Lakes and Ponds.
Hi, Dave.
You called out trends due to climate change with increased discharges in the winter and in the summer months. And I guess each of those bring with them phosphorus. Can you compare the summer phosphorus loading and the winter phosphorus loading and the trends in those?
Yeah, great question. We can, and I have. The thing about the winter is, unfortunately, it's really what we call undercharacterized, which is a fancy way of saying we don't really know because we don't typically monitor as intensively during the winter, at least historically. And we're changing that. We have an ongoing study with the University of Vermont to do a better job of monitoring throughout the winter period and trying to quantify these winter snow melt events or rain on snow events that are really delivering a lot of phosphorus. So I don't have something to show for you today, but I will say that the trends of phosphorus delivery are going to track the trends of discharge. So you're seeing more water in the winter because of different precipitation patterns, more rain rather than snow. Less water in the spring because there's less snowpack, and then just higher kind of episodic or high flows for summer storms. So that might be a bit of an unsatisfying answer because I don't have plots to show you, but I do have some analyses on that, and we're funding a study to look at the winter period more specifically.
All right, thanks.
Thanks, Dave.
Is
Thank
someone
you.
reading in the chat?
I was just gonna go read the questions that are now in the chat. One was asking if there are any plans for more monitoring buoys and rivers.
Oh yeah, there are. So we have, at the time of the flood, we had a buoy, as I said, in the Lamoille River and in Mallets Bay. We have another one in partnership with SUNY Plattsburgh in the main lake, just south of Valcourt Island. And then we also have collaborated with the University of Vermont to kind of repurpose their buoys that are deployed in Missisquoi Bay and in St. Albans Bay. So those will be redeployed this year. And then we are currently in the process of purchasing an additional buoy to be deployed in the Northeast Arm segment, right at our long-term monitoring station there. And that will be unique because it will have a profile or a string of sensors that will be measuring temperature and dissolved oxygen all the way to the bottom of the lake in the Northeast Arm. So yeah, we're expanding that network every year. All right, thanks, Julie. I'm seeing the chat now.
And then it also looks like there is interest in hearing about your wastewater analysis, as well as any initial results you might have to share on the impact of the December flooding.
Okay, sure. Yeah, I'll start with wastewater. So just acknowledging that there were huge impacts to wastewater infrastructure and several wastewater treatment plants that went offline. So that is something that those communities are working through and trying to become more resilient in the future. There was a significant sewer line break in the Burlington that ran underneath the Winooski River. Which was, let me pull up my notes on that one. So that, was delivered, that was leaking untreated waste to the Winooski River, which of course is a great concern, mostly because of the potential for pathogens to be in the water. So there are bacteria and viruses that can make you sick, of course, with untreated water. This is water that went down drains, people's faucets and bathtubs and toilets, of course. So that is a concern there. What we did not see was, widespread bacterial contamination as a result of this flood. Burlington, as far as I know, was testing daily for at least a week following the flood, and we're below the EPA threshold for E. coli for that entire monitoring period. I think near the mouth of Winooski River, there were some elevated counts, and there was an advisory, issued to not swim or recreate within a mile of the mouth of the Winooski River, which is appropriate precaution. But we did not see, widespread contamination for the lake. This was really kind of localized and focused on the areas that had this impact. And I did do some math for the Burlington leak that, was resulting in about 200,000 gallons of untreated wastewater entering the Winooski River every day. That's a lot of untreated water, right? That's more, we want to see 0 untreated water. So that is alarming. And I put that in context with the about 23 billion gallons of water per day that the Winooski River was delivering. So the wastewater, the untreated wastewater was about 8/10,000ths of 1% of the total flow. So 200,000 gallons, that's more than we want to see. And there is so much water moving down the Winooski. It was a very small fraction of the total flow, and it did not result in a widespread contamination. So just some thoughts to put it into context. Of course, we want that to be wastewater lake to be 0. We want all of our infrastructure to be resilient to these types of floods. And the Burlington DPW worked really hard to address that issue and got it fixed in a timely manner. If there's other questions on that, I can talk about it.
Thank you. And then I think it looks like the last question we have is, the TMDL targets have an end date of 2036. Do storms like the one in July suggest we need to make any approaches to how we are attempting to reduce phosphorus?
Make any approaches. Maybe this person means adjustments or changes. Okay, yes, thank you. So as of now, we are still, holding the course. What we know is that storms like this can be a setback, right? When you have restoration projects in place, they can get overwhelmed by a storm like this. But as I said, that we do have the margin of error or margin of safety in the TMDL, and all the efforts we're doing are all focused on reducing phosphorus. So there has not been discussion that I've heard of, updating the TMDL, numbers or allocations for Vermont. There is discussion on reviewing them and renewing them for New York. So New York is beginning that effort to update their phosphorus TMDLs for Lake Champlain. But as of now, our partners are continuing our efforts to not only invest in projects that will reduce phosphorus loading, but also improve our tracking of those reductions. And also in everything we're doing, we're focusing on resilience to flooding like this.
Great, thank you. And with that, it's 1 o'clock, so I thank you all for coming. Be on the lookout for a follow-up email with a feedback survey, as well as the links that were dropped in chat and today's presentation slides. Have a great day, and I hope to see you at our next conversation in April.
All right, thanks all. Thanks, Julia.
Thank
Bye.
you, Matt. Thanks,
Thank
everyone.
you.
Take care.